Hi everyone, I'm Luca and this is Harnessing Large Language Models for Training-free Video Anomaly Detection, a joint work with Billy, Massimiliano, Yiming and Elisa. The goal of video anomaly detection is to identify unusual activities in a video and the temporal window in which they occur. Depending on the level of supervision, video anomaly detection methods can be classified into four groups: supervised methods, which rely on frame-level labels to distinguish normal from abnormal frames; weakly supervised methods, which have access to video-level labels; one-class methods, which train only on normal videos; and unsupervised methods, which do not rely on predefined labels and exploit both normal and abnormal videos. However, every existing method requires a training procedure to establish an accurate video anomaly detection system, and this has some limitations. First, a VAD model trained on a specific dataset tends to underperform on videos recorded in different settings. Second, the acquisition of data can be challenging, especially in video surveillance applications, where privacy can hinder data acquisition. So this led us to investigate a novel research question, that is, can we develop a training-free video anomaly detection method? And the answer is yes. In this work, we propose language-based video anomaly detection, also named LAAD, a model that combines existing vision language models with large language models for training-free video anomaly detection. Let's see each component of the proposed LAAD one at a time. Given a test video, we first employ a captioning module to generate a scene description for each frame. However, the raw captions can be noisy, with broken sentences or incorrect description. Therefore, the use of these captions to estimate anomaly scores would lead to unreliable results. For example, see the frame on the right within the ground truth anomaly area. The caption of this frame does not accurately represent the visual content, leading to a low anomaly score given by the LLM and a wrong classification. To address this issue, we exploit modality-aligned vision language encoders and form a set of caption embeddings by encoding each caption in the video. Then, for each frame, we find the semantically closest caption using the cosine similarity and replace the original caption. The caption sequence that we obtain is cleaner than the initial sequence, however it lacks temporal information, so we leverage the LLM to generate temporal summaries. In particular, for each video frame, we form a video snippet centered around the frame, and we extract a caption subsequence. We then query the LLM with this caption subsequence and a summary prompt to get the temporal summary. We finally ask the LLM module to assign a score to each temporal summary in the interval 0–1, where 0 means normal and 1 anomalous. We obtain in this way the initial anomaly scores of the video. However, these scores are purely based on the language information encoded in their summaries. Therefore, we refine them by aggregating scores from semantically similar frames. In particular, given a frame, we encoded the video snippet that we obtained in the previous step using the video encoder. Then, we find the set of k temporal summaries that are most aligned with this video snippet, and we finally obtain the refined anomaly score as a weighted sum of these scores, where the weights are obtained by softmaxing the cosine similarities. We validate our training-free method on the UCF crime and XD violence datasets, which include videos featuring real-world surveillance scenarios, and we compare it with state-of-the-art video anomaly detection methods that are trained with different levels of supervision, as well as training-free baselines that we introduce based on VLMs. Our method, without any training, achieves superior performance compared to both one-class and unsupervised baselines on both UCF crime and XD violence. In this slide, we show qualitative results obtained by LAAD on 2 test videos. For each video frame, we plot the anomaly score computed by our method, and we display the semantically closest temporal summary. In both videos, we can see that when the anomalies are occurring, the temporal summaries of the frames accurately represent the visual content, which enables LAAD to correctly identify them. You can check our project page and code for more results and ablation studies. Thank you, and I hope to see you at the conference.